Okay, it's 12 o'clock. Let's continue talking about what we were talking about last class. And we ended on the fact that the square root of omega, an infinitesimal, is actually at a higher level. Than omega. Okay. So when you take the square root of an infinitesimal, it actually gets larger. Okay. I said that I would record a lecture and upload it, and I didn't do that because I thought maybe it's best that we just keep it in class just in case you guys have questions. It was one class period anyway, so it's not that big a deal. So that's why 1.2 has not been uploaded. We're still in the midst of 1.1, but we're about to finish that up and move on to 1.2. As you know, the syllabus is tentative, so we'll move as we can. Okay, so let's compare and contrast. Which one is at a lower level? Let's see, 3 omega or 47 omega cubed. Which one do you guys think is on a lower level and why?
47 omega cubed.
Why?
Because it's cubed.
Because it's cubed?
Yeah.
What does cubing an infinitesimal number do to it?
Well, the higher like the thing, it goes lower.
Higher the power?
Yeah.
The lower the level?
Yeah.
Yes, yes. Because remember, we had the reals, and let's say here's 0. When you zoom into the left and the right of 0, hidden is the omega level. The whole omega level, omega, 2 omega, negative omega, negative 2 omega. All of this is hidden right there. But as you've noted, you can go even further and even further here to the omega cubed level, where this would occur here. And this would be our omega squared, 2 omega squared. And over here, where this would be our 0, this would be our omega cubed, our 2 omega cubed. And of course, the negatives. So you are indeed correct that this is on a lower level. Very good. So we agree that omega is very small, right? We agree it's very small. So what about 1 divided by that number?
Capital omega.
Oh, you guys have been reading your books. Very good. What is capital omega? So this young man, what is your name?
David.
David. This young man, David, asserts that this equals capital omega. But he has yet to give an exposition on what capital omega is. Do you care to describe us to the class what capital omega is?
Isn't it like an infinite? So it's the infinitesimal in the opposite direction.
It is an infinite number. Infinitesimal is an infinitely small number. Capital omega is an infinitely large number. Okay? So this makes sense because whenever you divide smaller and smaller numbers by, say, 1 divided by 0.1, notice that's 1 divided by 1 over 10, which when you reciprocate it, it becomes 10. Just like 1 over 0.00, or just 0.1. Notice that this is 1 divided by 1 over 100, which when you take its reciprocal, it becomes 100. Notice that if you continue, 1 divided by 0.001, this is the same thing as 1 divided by 1 over 1,000. When you take its reciprocal, it becomes 1,000. So 1 divided by a smaller and smaller number gives you a larger and larger fraction. So if you divide by an infinitely small number, your fraction becomes infinitely large. This omega here is infinitely large, and hence why we do capital omega. Very good. So actually going back here, we have the real level, and now we have the capital omega level. And guess what? There's going to be omega squared low. And yeah, omega cubed low. With this happening, all of the reals actually fit into a tiny sliver of the omegas. There's omega. Here's 2 omega. There's negative omega. There's negative 2 omega. All of the reals are actually just in tiny sliver, to the left and to the right of that. Okay, so let us prove that this is true. Let's prove that 1 over little omega is capital omega is equal to an infinite number. How do we characterize an infinite number? Well, if we say omega is infinite, that implies for any real number, let's say it's positive and it's non-zero, for any real number you can ever pick, that this is true. And clearly, this would be true as well. Be greater than 0 because it's positive. Right? Pick any really big number. Give me one. Someone. A million. Oh, yeah? Well, I'm on capital omega, and I'm a million plus 1. Pick a larger number. A trillion. Oh, yeah? I'm omega. Capital omega, and I'm a trillion plus 1. This is what happens. Okay, so let's prove its existence. We have to prove in general that this omega exists, and that it's actually 1 over little omega. So here's our theorem. 1 over omega is infinite, i.e., for every positive real number, 1 over omega is greater than r, which is greater than 0. This upside down A just stands for every. So I'm going to highlight this equals for every. In mathematics, we say for every so much that we've created a symbol shorthand for it. And this thing, R, epsilon, reals, this just means it's an element of the reals. It just means it is a real number, a positive real number. So R is a positive real number. This is what this symbolism means. Little r is a positive real number. And now that I've explained what that notation is, let's prove it. Here's a proof. Okay. So, by hypothesis, R is an element of the positive reals. But that implies that 1 over R is also an element of positive reals, is it not? Take a positive real number, 4. Well, then 1 over 4 is also a positive real number, right? Okay. We claimed that omega is an infinitesimal. And recall, by definition, that implies that for any positive real number, this is true. If omega is an infinitesimal, then for every positive real number, it is smaller than it. So let's just look at this inequality right here. Omega is less than 1 over r. Notice what happens when we take both sides of this inequality to the negative 1 power, meaning we take the reciprocal of both sides. Then we get 1 over omega something r. And I'm going to tell you that it flips. But I haven't told you why. And here's why. Notice that 3 is greater than 2, right? Let's take the inverse of both sides. Then I get 1 over 3 is something to 1 over 2. Is 1 over 3 greater than 1 over 2? It's smaller, right? So it seems like when you take the reciprocal of both sides, the inequality flips, does it not? This is true in general, that every time you take the reciprocal of an inequality, it'll flip signs. Very much like when you multiply or divide by a negative number, it'll flip signs. So taking the inverse of this, we get this. What is, oh. Yes, we haven't taken the inverse yet. Here's the inverse. Here we go. There we go. So in turn, R was always greater than 0, right? So bam, we've proven that 1 over omega is an infinite number because it's greater than any possible real positive number that's non-zero. So we've proven it. So there's our proof that capital omega exists and that capital omega is infinite. So what can we take from that? We can take that 1 over little omega is capital omega. And that 1 over capital omega is what?
So 1 over capital omega?
Yeah. If 1 over little omega is equal to capital omega, then what is 1 over capital omega? Little omega. Yeah, because we take the reciprocal of here. Equations don't change when you take the reciprocal of both sides. Inequalities change, but equations don't change. Okay? So our takeaway is that the reciprocal of an infinitesimal is an infinite number, and that the reciprocal of an infinite number is an infinitesimal number. We'll be talking about this a lot. So let's do some examples. What about omega plus 4 minus 5 omega? What does this equal? Well, with infinite numbers, our arithmetic under the hyperreal number system is retained. It's just like normal arithmetic. So this is just like omega minus 5 omega plus 4. You just add like terms. So what do we get? Negative 4 omega plus 4. Easy as that. Okay. Let's do 43 omega minus 7 omega plus pi. What do we get here? Well, what's 30 what? 36? What's 43 minus 7? Okay, I'm not good at mental arithmetic either. Is that right? No, I think you're right. It's 36. Oh. See, I told you I'm not at mental arithmetic. And yet I've done theoretical nuclear physics research for the United States government. Because mental arithmetic is not what mathematics is all about. People make you think that when you're growing up because they make you memorize times tables and whatnot. But really, that stuff is not math. That is arithmetic. And if a computer can do it, then it's not that impressive, right? And what about 4 omega squared little omega? What do we get here?
4 capital omega.
Oh. How do you know that? The book.
So make capital omega times little omega equals 1.
Why though? It's quite a simple proof. Because remember this. It's as easy as that.
It's basically saying that times itself in a way.
Capital omega times little omega is like 1 over little omega times little omega. So the numerator and the denominator cancel. Because look, this is divided by 1. So you multiply across. And what you really end up getting is omega divided by omega. And anything divided by itself is 1, right?
Yeah.
Wrong, not 0 divided by 0. Remember that?
Yeah.
Typically, yeah, anything divided by itself is equal to 1. Yeah? I'm notoriously a troll, guys. Do you guys know what a troll is? Who here can tell me what you guys think a troll is? Don't you young people talk about that stuff? Trolls
On the video game.
on video games? What do you guys play? Pokemon? The young people playing Pokemon. Yeah. I think to me, what a troll is someone who likes to play tricks on people. That's what I would consider a troll, right?
Tricks when they keep going at it.
And they keep going at it. Yeah. Okay. What about omega cubed? What about capital omega cubed? Little omega cubed. Yes, it's 1. And there's many ways of seeing this. Well, this can actually be reformulated as this. Another way that it could be reformulated is as this. Either way. So what about 6 capital omega to the 5th omega squared? Very good. So the arithmetic is sinking in. You guys are comfortable with the arithmetic. So which is larger? Five omega or 2 omega cubed?
2 omega cubed,
Why?
because it's on a higher level.
It is on a higher level. When you cube a capital omega, it goes up. But when you cube a lowercase omega, it goes down. Yep. So we've got a definition here. Given A and B hyperreal numbers, A is on a lower level than B if A over B is equal to what? A is on a lower level than B. So they're both hyperreals, but A is on a lower level than B. What should their fraction be? A very big number or a very small number? Let's do an example.
Is it small?
A being omega squared and B being capital omega, right? This is definitely true. The numerator is on a lower level than the denominator, right? So what does this give us?
Little omega, so A.
Little omega.
Is it small?
What was the definition of capital omega?
1.
So let's convert that. So this is omega squared over 1 times the reciprocal of this. Omega over 1 when we multiply by reciprocals, what do we get? Yeah, little omega cubed, right? Which is what? Lower. Yeah, so this becomes infinitesimal. Another way to think about it is, 0 divided by any kind of number. 0. And 0 is approximately an infinitesimal. We'll talk about approximation in the next section. A is on a higher level than B if A B over B equals what? I need to flip these. B over A equals what? So A is on a higher level. Over there, A was on a lower level. Over here, A is on a higher level. But A is now in the denominator. And B is in the numerator. And A is at a higher level, and B is relative to it on a lower level. What does this become?
Infinite.
We'll see. Why? Why is it infinite? Let's do an example. Doing an example would be as if we put a higher level term down here and a lower level term down here, right? A is on a higher level than B. Over here, A was on a lower level than B. And it was on top. Now A is at a higher level on B, and it's in the denominator. What do we get here? Yeah. We multiply by reciprocals. So what should you get? An infinite number? No, you get an infinitesimal number. So think of that as like some number divided by infinity. You typically get 0. And 0 is approximately an infinitesimal. That's how you can think of it. What level is 5 plus 2 omega?
Yeah, so like under the real number, like what level will it be? Or
What level is 5 plus 2 omega?
Unlike the regular level?
I'm not asking you what level is 5. I'm not asking you what level is 2 omega. I'm asking you what level is 5 plus 2 omega. Compared to 5, is 2 omega significant?
No.
It is?
Doesn't that decide the level it's on? The omega.
what level will it be?
When you look at them separately, you notice that 5 is a real number, 2 omega is an infinitesimal. So it's on a lower level than 5. It's insignificant compared to 5. It's infinitely small. So we'll talk about approximations in the next section, but this is approximately just 5. So the level that it's at is the real level. Yeah. Remember, omegas are very, very, very small numbers. They're basically 0. Even like 5 billion omega, even like, even this number, this is approximately 0 when you compare it to a real number. They're very, very small. Does that make sense? So when we ask you what level is this on, we look at the highest level term, and that's the 5. So what about 3 omega squared plus omega minus 8? What level is it on?
8.
It's on the -8 level. So you're saying it's on the real level. Is that what you're trying to say?
Real level, but you would still include the capital. I mean,
Omega squared.
like after you do it, you would put it out, and then you would put the approximately -8, but it'll still be on the real level. But wait, negative is still.
I don't know. You guys still thinking it's on the real level? Or maybe you having some doubts?
I haven't doubt.
You having doubts?
Because they go to negative.
Well, isn't it? No, because wouldn't it be capital omega squared because all of the real numbers exist inside of it?
Is it on
Yes.
the omega
Capital
squared?
omega squared is the highest level term. This one and this one are insignificantly small compared to it. This whole equation is approximately this. We'll get to approximation in the next section. Yeah, because recall, here's real, here's the omegas, here's the omega squareds.
Okay.
But down here is the little omegas and their powers. Recall right here is omega to the 1/2, which is the same thing as the square root of omega. Where would the square root of capital omega be?
Right there.
Yeah, kind of where I've highlighted it, right? No. Trolling again. It'd be over here. It would take you closer to the reals.
Oh.
Just like square rooting little omega takes you closer to the reals, square rooting capital omega actually takes you closer to the reals. So, the homework that is assigned will give you copious amounts of practice with this stuff. So now let's talk about a very important aspect of this whole theory is the transfer principle. This principle is the reason why we can discuss hyperreal numbers to begin with. It says all algebraic formulas the real numbers are true for are also true for hyperreal numbers. This makes a lot of sense because the hyperreal numbers actually live inside the real numbers. By hyperreal numbers, we actually mean the omega, little omegas. The capital omegas have the real numbers living in them. So for example, this is an inequality that is true for the real numbers. Is it not? People who've taken trig, recall that sine parameterizes the y values on the unit circle. The highest point sine can achieve is 1. The lowest output sine can give you is -1 because it parameterizes the y. So yes, this is absolutely true that the sine of x for x is an element of reals or real numbers. The output is wedged between -1 and 1. This is analogous to saying that the range of the sine function is -1 to +1 inclusive. But notice the transfer principle implies that this is true for such an inequality like this. That sine of 47 capital omega minus 500 plus 2 little omega squared is in between -1 to 1. The transfer principle says that this holds. There is a proof for the transfer principle, but that is graduate level mathematics. We are right now at undergraduate level mathematics. Okay, so that is 1.1. Let's move on to 1.2, approximation. Let's talk about the square root of 2. What do you guys think this number equals? One point something. That's not true. This number actually equals square root of 2. It can be approximated as 1.4, what else? 1, 4, 2. But those dots imply that that is just an approximation. The square root of 2 is actually an irrational number, meaning you can't represent it with a finite number of terms. The more and more terms you include, the closer and closer you get to the actual value of square root of 2. But we can never actually represent square root of 2, its actual value, with a decimal expansion. Our best bet is to just say it's a square root of 2. So let's talk about errors of approximation. So what is the error in assuming that the square root of 2 is actually equal to this number? That's what we aspire to find out. Well, one way to do it is to take the difference between the two values. So here's the approximation minus the actual value, which again is another approximation, but we'll assume that a higher order approximation can simulate the actual value, even though it's not its actual value. Notice when you do this, you get a very small negative number. This is your error. That means assuming square root of 2 is equal to 1.4142 in this construct is tantamount to being wrong by 0.000135562, which is a tiny amount relative to the order in which you're talking about, right? That's a tiny amount if we're in meters. It's a tiny amount when we're in meters. But what if we're in centimeters or millimeters? Still kind of tiny, but when you get to the order of micrometers, it's no longer tiny. It becomes a big error. And then when you get to nanometers, it becomes an even bigger error. So a good approximation is a relative construct. It's relative to the scale in which you're operating. Some ancient mathematicians approximated pi like this. And you can approximate pi as 3.14. But really pi, 3.14159.265, you know, ... What is this? 22/7 is approximately 3.142 0.285714. Notice when we take the errors here, their difference, I'm subtracting this from this. Take this and subtract it from this. The error is 0.00126449 ... So again, not that bad of an error. Why are we talking about this stuff? Well, we wish to understand what is 7 plus omega approximate to. Well, let's consider what is 7 equal to, and what is 7 plus omega equal to. 7 is equal to 7.000 forever with O's, right? And then 7 plus omega is what?
7 something.
Same thing. Same thing. So if you were to subtract these two, the error in approximation, assuming that this value is slightly larger than that value, multiplying, and so when you subtract it, you get a slightly negative number. This is the error. You get a slightly insignificantly small negative number as an error. So what does that mean? Does that mean it's a good approximation or a bad approximation? It's a very good approximation. It's an infinitely good approximation. Meaning 7 plus omega is just approximate to 7. And we can be confident of that approximation. So what is relative percent error? To 100% times your error divided by the actual value. So the relative percent error here with the pi stuff would be 100% times that 0.00126449 divided by actual value 3.14159.265. This becomes a percentage. Even the percentage is approximately 0.04%. This is the error in estimating pi as 22/7, which is pretty astonishing. And from now on, I will just estimate it as 22/7. Based off of purposes, because your error is only like 0.04. Unless you're making very small objects, then that error will not come back to bite you. So what would be the relative error here? Well, it's 100% times the error divided by the actual value. Notice the top is basically 0. So this becomes approximately negative 0.000%. So the relative error is infinitesimal. The relative percent error is infinitesimal. So approximating 7 with 7 plus omega is infinitely correct. So it's an infinitely good approximation. Whereas 22/7 can break down at some point. That one can't. Relative to the reals. Relative to omega squared, it definitely can. Little omega squared. All right. Yeah, I gotta say little omega when I mean little omega and big omega when I mean big omega. So what does this approximate to?
That's 0.6.
Say what?
So it'll be 31.6.
39.6. What does this approximate to? Ah, why? You must justify why you believe this is true.
Because it's like what we did over there for the 7. Whenever you're doing it, it give you lesser error. I get you'll be closer to the real number, but you still have your
It's because this is a real number and it is on a higher level than these two numbers. That's the answer. That's the short, sweet, to the point answer, is that this is at a higher level than this term and that term. Therefore, those terms that I underlined are insignificant compared to the 39.6. So they're approximately 0. So this approximates to 39.6. Okay. Where is this number located at? In the hyperreal number system, where can we find this number? And I really like this part of the textbook. It's very beautiful. Let's find it where it's at. Here's our 0. All the way over here is our 39.6. Okay. So here we are, but this, when you zoom in, you got the omega level over here, okay? And right under it is this 39.6, okay? And to the left would be something like 39.6 minus omega, 39.6 minus 2 omega. But to the right would be 39.6 plus omega. And even more to the right would be 39.6 plus 2 omega, right? So we're getting closer to where the location is, but we have to go down even a further level to the omega squared level. When you come directly down right here, you're at your 39.6 plus 2 omega. When you go to the right, it'd be 39.6 plus 2 omega plus what? Very good. But our number is minus omega. Yes. That's where our number is at. 39.6 plus 2 omega minus omega squared is right there. It's in the real numbers, but its hyperreal components span 2 different additional infinite levels, infinitely small levels. Very cool. Very cool. So what about 27 omega plus 3 omega squared? What does this approximate to?
27 omega.
Yes, Why?
Highest level.
Out of the two, even though 27 omega is very small compared to the reals, compared to the 3 omega squared, it's very large and it wins. So 27 omega is what that approximates to. What about 35 minus 8.4 omega? What does this approximate to?
35.
Why?
It's on the real level.
And the real level is what?
Higher than that.
There we go. So here's a definition. Let x and y be hyperreal numbers. Suppose is non-zero. We say x is approximately y if y minus x over x is equal to 0 or infinitesimal. We also say 0 is approximately 0. And 0 is the only number that is approximately 0. Does this definition make sense? We'll see. This definition makes sense because if x and y are on the same level and we take their difference in the numerator, their difference is 0, which gives you 0 if they are identically the same. Or their difference gives you an infinitely small number if x is greater than y or y is greater than x or vice versa. You'll get an infinitesimal number as a result. It could be a positive infinitesimal, it could be a negative infinitesimal, depending on which of these is greater than the other. But either way, given that they're both infinitesimal, this will happen. For example, let x equal omega, y equal 2 omega. Right here, we would get 2 omega minus omega over omega. Notice this becomes omega over omega, which is 1. So we cannot say that omega and 2 omega are approximately the same because it didn't equal 0 or an infinitesimal. We can't say that they're approximately the same. But if x is equal to 2 omega, y is equal to 2 omega, then you get 2 omega minus 2 omega all over 2 omega. Here you get 0 over 1, which is 0. So yes, we can approximate 2 omega with 2 omega. Okay. So this is like an equivalence relation, all right? But approximation can also be like an operation. So here's a theorem. If x is on a lower level than y, that implies that y plus x is approximately y. Recall, x and y are hyperreal numbers. Well, why is this the case? It's because, well, we can actually do it two ways. Y plus x is approximately y is the same thing as y is approximately y plus x. Notice that when we take the definition of approximate, we can say that the right term y, which is the y plus x now, minus the left term x, which is y here, all over the left term x, which is y here. Notice the y's will cancel, leaving x over y over here. Notice that x over y is what? X is on a lower level than y. So this equals what? Remember the a and the b and the b over the a? Yes, this equals an infinitesimal. So it actually satisfies this definition for two hyperreal numbers being approximately the same. So this hyperreal number y is approximately the same thing as this hyperreal number y plus x. Notice it could have been done in reverse as well. We could have done it could have been done like this as well. What you would just get is you'd get x over y plus x, which again approximates to an infinitesimal. So now that we've talked about one being on a lower level than the other and one being on a higher level than the other, well, I'll say one last definition before I let you guys leave. For hyperreal numbers, x and y, are on the same level if x over y is equal to r, some element of the positive reals. So remember when we did that example, we said, what if x is equal to 2 omega and y is equal to omega? And we took their ratio, x over y would then give me 2 omega over omega. Well, notice omegas cancel and you get a 2. 2 is an element of the positive reals, which means that 2 omega and omega are on the same level because their ratios equals a positive real number. Makes sense? Because they're both on the omega level. Omega and 2 omega are all on the same level. Here's omega level, here's 0, here's omega, and here's 2 omega. They're both on the same level. Therefore, when you take their ratio, they'll output a positive real number. If they don't do that, that means that they were on different levels. If you take their ratio and they output an infinitesimal number, That means the numerator was on a what? Smaller level, right? If you take their ratio and they output an infinitely large number, that means the numerator was on a what? Compared to the lower, compared to the y. The numerator was on a higher level. Yes. You guys can leave. Your homework for 1.1 is due on Friday in class.